Hello, and thanks for using TickBoom. For this question, I've been asked to tackle question 10, and in particular focusing on part D. But the way this question is written, I'll have to work through part A, B, and C, because it's in working out those parts that you can then get your head around part D. So I will work through it all, but the main focus is on the technique that we can use to tackle part D. It actually comes from the Cambridge Math textbook for Extension 2. So it's the Year 12 Extension 2 textbook. It's the complex numbers topic, and it's exercise 3C. And it's in the way these textbooks are set up, you have a kind of level of grading of questions. So you have your basic questions, and then what they call development questions, where it gets a little harder, and then enrichment questions, which are the hardest parts. This one falls under the development, so not the ultimately hardest type of questions in this textbook, but this question definitely is on the harder end of the spectrum, and it does take quite a good understanding of Argand diagrams and complex numbers to be able to tackle it. So basically, the way the question reads, we're told to let W equal cis 2 pi on 9, and that's just a shorthand way of writing a complex number as cos 2 pi on 9 plus I sine 2 pi on 9. From there, we're told to show that W to the power of K, where K is an integer, that's a solution of the equation Z to the power of 9 equals 1. Then we're told to show that W plus W squared plus W cubed all the way up to W8, that the sum of all of that is equal to negative 1. Then we're asked, hence, so using what we've kind of just worked out, show that cos 2 pi on 9 plus cos 4 pi on 9 equals cos pi on 9. And then finally, we're told to deduce that cos pi on 9 times cos 2 pi on 9 times cos 4 pi on 9 equals 1 on 8. And, you know, whilst you could just get your calculator out and do that, clearly that's not what would get you the marks in a question like this. And there are also ways you could prove this without using complex numbers at all, but again, I don't think that's the nature of this question. The way the question's written, it's really leading us to make use of what we've just shown to deduce this particular result. So that's what we need to deal with. I'll just start, so I'll write out part A. So what we're being asked is to let W equal cis 2 pi on 9. And really what that is, as I mentioned, it's cos 2 pi on 9 plus I sine 2 pi on 9. That's really, this is just a shorthand version of writing the longhand form of a complex number. So part A is saying to show that W to the power of K is a solution to Z to the 9 equals 1, which is really Z to the 9 minus 1 equals 0. That's the kind of format that will be helpful for us. Now, where to start for this is, let's work out, well, what is W to the power of K? So W to the power of K, we know we can write that as cos K times 2 pi on 9 plus I sine K times 2 pi on 9. And we know that using DMT or de Moivre's theorem. So that's kind of the essence of getting W to the K in a format that's useful. But now what we can do is say WK to the power of 9, and we'll use de Moivre's theorem again. So we'll get cos, and we'll put 9k times 2 pi on 9 plus I sine 9k times 2 pi on 9. So that's wk to the power of 9. Now notice these 9's can cancel. So really what it becomes is cos 2 pi k plus I sine 2 pi k. And remembering in this case k is an integer. Now it can be helpful at this point to remind ourselves of what the cos and sine charts look like. So I might just draw up an axis here. And I might I'll make this particularly long just to demonstrate the point that I'm trying to show. So I'll just call this x and y. We'll call this 1, and we'll call this -1. And we'll go pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and that's probably enough to demonstrate the point. What I might do, I'll start by plotting y equals cos x. I might do that in black. So y equals cos x, it'll start at 1, we'll intercept at pi on 2, come down, and then it follows this recurring pattern. So I'll just label that y is equal to cos of x. And then in, maybe I'll use red, I'll draw sine. We'll draw the sine curve. And so that starts at 0 and will come up. And then down. And it follows essentially the same pattern, it's just shifted across. And whilst this is a kind of, I guess, a fundamental thing to know, it does come in handy to remind us of this, which is why I'm taking the time to write it up. But just by looking at these curves, we can see that, at least with cos, every time we're at 2 pi, or 4 pi, or 6 pi, any multiple of 2 pi, which is really what we're dealing with because k is an integer, so we're dealing in multiples of 2 pi. For the cos curve, the black line, at 2 pi it's 1, 4 pi it's 1, at 6 pi it's 1, and that pattern will continue at every multiple of 2 pi k. So what we'll see is that cos 2 pi k is equal to 1 for all integer k, alright. Now if I focus on sine 2 pi k, at 2 pi sine is 0, the red curve is 0, at 4 pi it's 0, 6 pi it's 0, it's equal to 0 for all integer k. So what we can do is come back up to our w to the power of k to the power of 9 and see that this will be 1 and this will be 0. So we can say therefore w to the power of k to the power of 9 is equal to 1, which means w to the power of k to the power of 9 minus 1 is equal to 0. And that is the format that we had here. Essentially we're inserting wk in for z, which means that w to the power of k is a solution to z to the 9 minus 1 equals 0, which means it's a solution to z to the 9 equals 1. So that's part A done. That's what that question was asking us to demonstrate. Now if I move on to part B, so part B was asking us to show that w plus w squared plus w cubed all the way up to w8 the sum of all of that is equal to -1. So that's what we need to show. Now, where we can start here is knowing that z to the power of 9 minus 1 equals 0. That has 9 roots, and they all lie on the unit circle. And what will be really helpful both for this part and for the remaining parts of this question is to draw up that unit circle and plot these 9 roots. So what I'll do is I'll just draw up a chart. So this will be an Argand diagram, so we'll have our real and our imaginary axis. And I'll just plot points 1 so that I can draw up my unit circle. I'll do my best to make this a half decent circle. Okay, so this is our unit circle. It goes 1, minus 1, minus 1, 1. So what we know is that z to the power of 9 minus 1, all of the roots of that will lie on this circle. And we know from part 1 that w to the power of k, where k is an integer, is the solution to z to the 9 minus 1. So all of these roots are going to be w to the k for various values of k. So what I'll do, the first root, I'll call it z1. That will be equal to w to the power of 1. And that's going to be equal to, I'll just use the shorthand cis, 2 pi on 9. Now if we just get into our calculator and go 2 times pi, or 180, divided by 9, that's going to plot onto this unit circle at 40 degrees. So I might just use a different colour. So this is 90 degrees, 45 is about half, so 40 is just a bit less than half. So that's my Z1. And we know this angle here is 2 pi on 9. And we know that all of these 9 roots, they're going to plot at equidistant points around the circle. So we're essentially going to be dividing this circle up into 9 equal chunks. But what I'll do is I'll work through methodically all of these 9 roots and lay them out, just because it's going to be both useful for this part B, but also for the rest of the question. So I might just write them all out. So we'll go Z2 equals W squared equals cis 4 pi on 9. Z3 equals W cubed equals cis 6 pi on 9. Z4 equals W to the 4, which equals cis 8 pi on 9. Always going up by 2 because it's 2 pi k. Z to the 5 equals W to the 5 equals cis 10 pi on 9. Z to the 6 equals W to the 6, which equals cis 12 pi on 9. Z to the 7 equals W to the 7 equals cis 14 pi on 9. z to the 8 equals w to the 8, which equals cis 16 pi on 9. And then the last one, z to the 9 equals w to the 9, which equals cis 18 pi on 9. And that is 18 on 9 is equal to cis 2 pi. And coming back to our cos and sine charts, we know that at 2 pi, the cos part will be 1, the sine part will be 0, so that's going to be equal to 1. So what I'll do is I'll just plot all of these. We know that each time we're moving another 40 degrees, so Z1's at 40, Z2's at 80, so if this is 90, 80 will be about here. It doesn't need to be perfectly accurate, but you kind of want it to be in the ballpark so that you can get the right idea. So 40, 80, 120, I'll kind of put about maybe here. So that's going to be Z3. 40, 80, 120, 160. Let's try that about there maybe. That's going to be Z4. And what I'm going to do is just draw some dashed lines, vertical lines down here. So this will be somewhat helpful to remind ourselves. Basically, the remaining points are all going to be conjugates, well, apart from Z9, but the remaining points coming on their way back to the real axis are going to be complex conjugates. So it's helpful to know that they're just on the opposite side of the real axis. So we'll have Z5, Z6, Z7, Z8, and then finally Z9, which is the number 1 lying on the real axis. So I'll just fill in all those lines. Alright, so there's our unit circle with our 9 roots. You probably don't have to draw that up for this part B. It's helpful to know just to kind of make it very clear for ourselves what we're dealing with. What's probably worth pointing out is these Z5, Z6, Z7, Z8 being complex conjugates. So that's probably worth noting and reminding ourselves of. So Z5 is equal to the conjugate of Z4, which we can also write as W to the negative 4, because it's really cis negative 8 pi on 9. So if Z4 is cis 8 pi on 9, so if we've gone all the way 8 pi on 9 to get to here, getting to Z5 is going in the opposite direction but the same angle, so it's negative 8 pi on 9. And that's going to be true for Z6, so Z6 is the conjugate of Z3, which equals W to the negative 3, which equals cis negative 6 pi on 9. Hopefully that's kind of making sense. So Z7 is the conjugate of Z2, which equals W to the negative 2, which equals cis negative 4 pi on 9. And then Z8 is the conjugate of Z1, which equals W to the negative 1, which equals cis negative 2 pi on 9. So that's just worth laying out. More just to remind ourselves for later in this question for part C or part D. But what I might do, I'll turn over. But the key to kind of proving what we need to prove is to note that all complex roots of unity they're going to add up to 0. So that's the kind of general result that we can use to get to this result, because W1 up to W9 are our complex roots of unity, so their sum must be 0. So what we'll get is, I'll just write it out in full. I'll go very step by step. So we'll go Z1 plus Z2 plus Z3 plus all the way up to Z8 plus Z9. That's going to be equal to 0. And as I've noted, Z1 is W to the 1, Z2 is W to the power of 2, and so on. So we can just insert those in. And remembering that W to the 9 is equal to 1, we can just replace that with 1 and bring it over. And that's how we get W plus W squared plus W cubed plus W to the 4. All the way up to W to the 8 is equal to -1. That's what we were required to show. So part B, not particularly complicated. We really just needed to know all the complex roots of unity add to 0, and then it's a very simple insertion. But it was worth taking the time to draw up this diagram and be very clear with what we're dealing with, particularly around these complex conjugates that we get, because that's going to be really helpful in the rest of this question. So now if we go on to part C, we've got the word hence, so making use of what we've just worked out. We want to show that cos 2 pi on 9 plus cos 4 pi on 9 plus, or is equal to, cos pi on 9. And this is where the question gets a bit more difficult, or at least you got to start to think of, or be really, really crystal clear on what you're dealing with. So let's just kind of start with what we know. We know from here, we know that Z1, and I'll just write this out in full because it's going to be helpful. Z1 plus Z2 plus Z3 plus Z4 plus Z5 plus Z6 plus Z7 plus Z8 plus Z9, all of that's equal to 0. We know that all the complex roots of unity will add to 0. But what I'm going to do is I'm going to strategically rewrite these in order so that I bring each of the conjugates together. So what I'll get is I'll get Z1 plus Z8, because they're conjugates. I'll get plus Z2 plus Z7, because they're conjugates. I'll get Z3 and Z6 plus Z4 and Z5, and then plus Z9 at the end. So that's all equal to 0. Now, one other thing I'm going to do, and we'll see why this is helpful very soon, I'm going to bring the Z3 plus Z6, and I'm going to bring it over with Z9. So we'll get Z1 plus Z8 plus Z2 plus Z7 plus Z4 plus Z5 plus Z3 plus Z6 plus Z9, all of that's equal to 0. Now what I want to do is focus on this Z3 plus Z6 plus Z9, because there's a way we can also determine that that is 0, and so we can drop it off. Now what we need to do is we need to start by noting that we can take Z to the 9 minus 1 equals 0, and we can actually factor that, because what it really is it's Z cubed minus 1 cubed equals 0. So we've got a difference of cubes, and if you, one thing you really should remember and kind of have committed to memory is that A cubed minus B cubed is equal to A minus B, A squared plus AB plus B squared. So that's something you kind of need to know. But using this result, we can now say effectively a is z cubed and b is 1. So therefore what we can write is z cubed minus 1 times z cubed squared plus z cubed times 1 plus 1 squared equals 0, which gives us z cubed minus 1 z to the 6 plus z to the 3 plus 1 is equal to 0. So really what we know is that our complex roots of unity, all of these roots, are essentially we can say the roots of z to the 9 minus 1 equals 0. What we can say is those roots involve solutions to z cubed minus 1 equals 0 and z to the 6 plus z cubed plus 1 equals 0. So what we can then note is that z cubed minus 1 equals 0 are the cubed roots of unity. So that's kind of, we're able to rely on similar results here, knowing that all of those cubed roots of unity would add to 0. So we can just ask ourselves, well, what are the cubed roots of unity? Which of these solutions are the cubed roots of unity? And, you know, when there's 3 roots, we're essentially taking our 360 degrees and dividing it by 3. So we're dealing with 120 degrees, 240 degrees, and then 360 degrees. So really we can come back to our diagram, and maybe I'll use red. We can pinpoint, so we'll go 40, 80, 120. Then we know, kind of can shortcut because we know we're going to get to the complex conjugate and then to 360. So Z3, Z6, and Z9, Z3, Z6, and Z9 are our cubed roots of unity. So what I can conclude is Z3 plus Z6 plus Z9 is equal to 0, which helps us simplify this, because therefore what we get to, coming back to our main thing that we're trying to show, is we get Z1 plus Z8, but remember Z8 is the conjugate of Z1, plus Z2 plus Z7, which is the conjugate of Z2, plus Z4 plus Z5, which is the conjugate of Z4. All of that is equal to 0. Now, using the result that when you add up complex conjugates, you essentially drop off the complex portion and double the real portion. What we then know is that 2 times the real portion of Z1 plus 2 times the real portion of Z2 plus 2 times the real portion of Z4, all of that is equal to 0. And now what we can do is, knowing that each of these z's are w to the k, and w, remember, is cos, the real portion is cos of the angle, and the complex portion is I sine of the angle, but we know they're dropping off, so it's really just cos. So where we get to is we get, therefore, 2 times cos 2 pi on 9 plus 2 times cos 4 pi on 9 plus 2 times cos Z4, which would be 8 pi on 9. All of that's equal to 0. And notice we're getting quite close, because we had 2 pi on 9, 4 pi on 9, and then pi on 9 over on the other side. So we're getting close. Now what I might do is I'll turn over. The first thing we can do is factor out the 2. So we'll get 2 times cos 2 pi on 9 plus cos 4 pi on 9 plus cos 8 pi on 9. all of that's equal to 0, which lets us drop off our 2. We just divide the 2 out. And now what we need to do is we need to kind of think about this cos 8 pi on 9. So what we can do is we can note that cos of pi minus x, in general the result for that would be equal to cos pi times cos x minus sine pi times sine x, and I think this result will become useful to us because what that is, if we come right back to our cos and sine diagrams, so this is kind of showing why this was useful to draw up because it's coming in handy. When I'm looking at the cos chart and I look at pi, -1, so cos pi is -1, so that would be -1 times cos x, and sine pi is 0, so that actually just drops off. So we've got basically, I'll just rewrite this, I'll just bring the negative over, we get cos x is equal to negative cos of pi minus x. Is a result that we can use to get this 8 pi on 9 into the format we're interested in, because what that means is cos of 8 pi on 9 is equal to negative cos of pi, which is kind of 9 pi on 9 minus 8 pi on 9. 9 pi on 9 minus 8 pi on 9 is pi on 9. So it's equal to negative cos pi on 9. So now we can insert that in, and what we get is cos 2 pi on 9 plus cos 4 pi on 9 minus cos pi on 9 equals 0, and then we just get our final result, which is cos 2 pi on 9 plus cos 4 pi on 9 is equal to cos pi on 9. So that's part C done, which brings us to our last part, part D, which is definitely the hardest part. We're told to deduce that cos pi on 9 times cos 2 pi on 9 times cos 4 pi on 9. We're told to deduce that that's equal to 1 on 8. And as I mentioned before, you can't just get out your calculator and type it in. That's kind of not what the question's asking you for. When I first was thinking about this, I really ended up trying quite a lot of different things. It was quite hard to kind of think of an elegant way to demonstrate this. I started by taking this cos pi on 9 result and inserting this, thinking that, you know, often you need to use the prior results, so let's just insert it and expand and see what we get. But that didn't really lead me anywhere. I did go down a bit of a rabbit hole where I kind of looked at the various triangles that got formed by these different results and, you know, thought about whether some other basic trigonometry could get us there. But that didn't really lead anywhere for me. It is possible to prove this using generic trigonometry, but again, I think the question wants us to specifically make use of the results that we've just demonstrated. So then where I finally got to is noticing the pi on 9, the 2 pi on 9, the 4 pi on 9. They all came, they all appeared in part C just before. And remember, we got there because we were adding a complex number with its conjugate. So I thought, well, why not just start there? Why not note that we know Z1 plus Z8 is equal to the Z1 plus the conjugate of Z1, and that's equal to our 2 cos 2 pi on 9. I'll call that part 1. We'll do our Z2 plus Z7 is equal to Z2 plus the conjugate of Z2, which gets us our 2 cos 4 pi on 9. And I'll call that 2. And then finally, we'll do our Z4 plus Z5 equals Z4 plus the conjugate of Z4, which equals 2 cos 8 pi on 9, which is equal to, as we just showed, minus 2 cos pi on 9. And I'll call that 3. Now, we've kind of got the various arguments that we want to see in our result, and they're all multiplied by 2, and notice what we're trying to deduce is multiplying 3 things. And I know if I go 2 times 2 times 2, we're going to get our 8, which means I think, or I eventually thought, what if we took 1 times 2 times 3 and tried to then get it into this format? So what we then get is we get 2 cos 2 pi on 9 times 2 cos 4 pi on 9 times negative 2 cos pi on 9. That is all equal to, and then we can kind of insert what we know. So it's Z1 plus the conjugate of Z1 times Z2 plus the conjugate of Z2 times Z4 plus the conjugate of Z4. And now the question becomes, how do we expand this into a form that's going to help us? And the hint, I think, of this question is what we had to show in part B. Because we know that the sum of w all the way out to w to the power of 8 is negative 1. If we can get this in a format that lets us show it's negative 1, then this will get us to our ultimate destination. So I think what we can do now is get all of this into our w format, and remembering that with our conjugates we can write that as w to the negative power. So what we'll get is w to the 1 plus w to the negative 1 times w to the 2 plus w to the negative 2 times w to the 4 plus w to the negative 4. And see how taking the time to write out our results on the unit circle to make it really clear we're dealing with complex conjugates, and just taking the time to note it all out very methodically has come in handy now for this part D. Because now what we can do is just, I'll do it very slowly and step by step, we'll expand out these brackets. So we'll get, first of all I'll expand these two brackets, so we'll go w to the 1 times w to the 2, so that's going to get us w to the 3. Then I'll go w to the 1 times w to the negative 2, and that's going to give us w to the negative 1. Now I'll do w to the negative 1 times w to the 2 is plus w to the 1. W to the negative 1 times w to the negative 2 would be w to the negative 3. We're just adding all the exponents. Now I'll expand this next part. So w to the 3 times w to the 4 is w to the 7. W to the 3 times w to the negative 4 is w to the negative 1. W to the negative 1 times w to the 4 is w to the 3. W to the negative 1 times w to the negative 4 is w to the negative 5. Plus w to the 5 plus w to the negative 3 plus w to the 1 plus w to the negative 7. Okay, now what I'll do is I'll keep all the positives, but for each negative we'll go and write that, noting that the negative powers, a negative power is just the conjugate of its equivalent. So we'll go w to the 7 plus w to the negative 1, what is that? So w to the negative 1 is Z8, because Z1 is the conjugate of Z8. So Z8 is equal to w to the negative 1. So plus W8 plus W3. Now w to the negative 5, notice I didn't actually write that out, but w to the negative 5 is really, if this is 5 and I did the negative of it, I'd get up to the fourth result. So they're always just conjugates, so you can always switch between them by taking the negative of their result. So w to the negative 5 is actually just w to the 4. Then we get w to the 5 plus w to the negative 3, which we had as 6, plus w to the 1 plus w to the negative 7 would be w to the 2. Notice here we've got 1, 2, 3, 4, 5, 6, 7, 8. So all of that is equal to negative 1. And that's making use of this result here. Alright, so, and I'll just write from part B to make that clear. Okay, I might just have to turn over, but really where we're at is where 2 cos 2 pi on 9 times 2 cos 4 pi on 9 times negative 2 cos pi on 9. All of that is equal to negative 1. So from there it becomes quite simple. We've got our negative 8, so 2 times 2 is 4, times negative 2 is negative 8. And I'll just write this in the order the question asked. So we had in the question pi, 2 pi, 4 pi. So we'll go times cos pi on 9 times cos 2 pi on 9 times cos 4 pi on 9. All of that's equal to negative 1. Let's bring the 8 over and we've got our result. Cos pi on 9 times cos 2 pi on 9 times cos 4 pi on 9 equals 1 on 8 as required. So that's that question. Definitely quite difficult, I'd say, particularly part D. Part C and part D, really. It's just required a real clarity of understanding of what you're really dealing with when you're dealing with the complex roots of unity. And what really became quite useful was fleshing out the fact that many of the roots, apart from the final one, they're all complex conjugates, and then knowing what that really means and what you can do with that, that allowed us to prove these two results using the results from the prior questions. So it's actually, as a question, it's quite a good example of all the things you can start to prove once you've got your head around the complex number system. So kind of going from the square root of negative 1 being undefined to then defining it to be this letter I, whilst that may seem like an arbitrary thing to do, it's quite amazing how from there you can then start to do so much with things like trigonometry. So yeah, quite an enjoyable question, a good challenge, definitely one to I think worth understanding. A lot of, in this Cambridge textbook that this question came from, often the textbook writers say, don't feel compelled to work through every single question. Kind of that would probably be overkill. But this particular one is definitely worth working through because I would say it's on definitely the harder end of the spectrum of what you'd probably see in your Extension 2 exam. If a complex number question like this came up on your exam, that would definitely be one of the harder types of complex number questions that you could get. That's what I would say. So hopefully you were able to follow along with all of that and it all made sense. I acknowledge it would be hard in the heat of an exam to think of this, but I guess the tip I'd have is always try and link what you're being asked to show with what you've just shown. And for me, what eventually the light bulb that went off was that these arguments were the same as what we just dealt with, so I could use the similar technique and just multiply them to get them in this multiplied format. So there you go, tick boom.